So yesterday we left off, we were talking about acidic and basic salts. Essentially, what you have to do is you have to look and see where that salt came from, okay? So if the K from the salt here would end up making KOH, which is strong, that means that that K is still going to be floating around and it's not going to grab a hold of anything, okay? So that came from a strong, that would end up, if there was an OH available to it, it would end up strong, and that OH would just be floating around, so nothing's going to get grabbed a hold. This acetate then, it comes from a weak acid. Okay, so there's your anion for acetate. I'm just not writing it out because I'm lazy. Okay, that, if water is available, it's going to split some of that water off. It's going to grab the H with that anion, and it's going to leave an OH behind. Okay, if you have more OH than you have H plus, what do you have? What situation? A base. So that's why they're called basic salts, because they are going to form a base condition when they are placed in water. That makes sense? Okay. Now the same can be held true of acidic acids, okay, or acidic salts. So if you have something like why did you turn over to an eraser? Here we go. Okay, why are you trying to be an eraser? You're not an eraser, you're a pen. There we go. If I have this guy, all right, I place him in water, the Cl is still going to remain dissolved. If there's an H that comes along, it's not going to grab it up, okay? It's just going to stay dissolved because it's chlorine. It's just going to float around in there. The NH4, though, is a weak base, so it will come along. It's going to donate an H to a water. So one of these H's goes to the water and becomes this, and it leaves this behind. Good, bad, ugly still. Explain again. Explain again. Okay, let's go back. It's okay. We can spend all day on this if we need to. All right. Remember, the first part of the year, I went really fast. I will go as slow as you need me to go through this stuff, okay? So don't get freaked out about it. All right, I've got my nitrogen. Yes? I have 4 hydrogens surrounding that nitrogen. Again, I'm not an artist. My apologies. This has a positive charge. Hello. Yeah, he's back there. He's the real tall guy back there. Hand it to him. Way back. All right. So I have this guy right here. He was attached to a chlorine ion. Okay. So he was bonded to a chlorine ion. So chlorine I'm just going to do as a box. Okay. I put these 2 things in water. My chlorine is still going to be floating around. It's just going to stay as an ion there. This guy, though, he is going to give off one of these hydrogens. So he ends up looking like this. So this is my NH3. He's going to give off one of those hydrogens, which is going to be picked up by this water. So now you've got water. That water, and I shouldn't do that. That's bad, bad lippy, bad lippy. That water is going to have an oxygen here. And now it's going to have 3 hydrogens attached to it, which gives it a positive charge. Remember your H plus concentration, that is going to be greater than your OH now. So you're going to have an acid formed. So floating around in that container, you're going to have this chlorine you are going to have your weak base and you're going to have your hydronium ions. And it's this that's increasing. That is why it's an acidic salt, because it's created this H3O+. Acids have more H3O+ than they have OHs. That's the definition of an acid. Because remember, if you have an acid, your H+ concentration is going to be greater than your OH- concentration. You've created, by putting this thing in there, that salt in there, you've created these things. You've pulled some of this water apart, or added to the water, actually. You've added to the water an extra hydrogen, making it H+. And at that point, your H+ is going to be greater than your OH, which means you now have an acidic condition. Now, why does that not happen up here with the neutral salts? Well, because when you put the sodium in there, it's going to stay as a plus ion. When you put the NO3 in, that's going to stay as an NO3- ion. Because when water comes along, it's not going to grab a hold of an OH and form this and leave a hydrogen behind, because it can't. That's a strong base. This can't grab a hold of anything and form something. The only way that can happen is to dehydrate the water off. All right. Did we do no, it didn't stay from yesterday. All right. I think I fixed this on your papers before I sent it out. This is supposed to be a back and forth arrow. Okay. This is supposed to be a back and forth arrow. Did I fix it on your papers? Do you have this?
It's just the arrows are just not there.
Oh, okay. All right. So I just didn't put them in. Sorry, y'all. All right. So if you predict that you're going to form a base, put this on the other side. If you predict that you're going to put an acid, put this on the other side. Relish the fact that your strong is just going to be a spectator. It's just floating around watching what's happening. And then write your HOH to make it easier to determine if you're making a hydrogen or a hydroxide. Figure out what you're forming. Okay, so let's look at this guy. Let's try to figure out whether this is going to be acidic, basic, or neutral. Okay, Na. Is Na, would that form a strong base if I were to put that in, if it had hydroxide with it? Yes. So we're going to ignore him. He's just going to be a spectator. Is acetate going to form, is that part of a strong acid? No. So it's weak. So if this is a weak, and I put that in water, if you want to do your HOH, that's fine. Whatever makes you happy. What part of the water is this going to grab onto? The hydrogen. So I'm going to form this. What it was left behind? The OH-. If I have formed more OH- than I have hydrogens, do I have an acid or a base? Base. So this is a basic salt then. It is going to form a basic condition when it is placed in water. All right. I have NH4 here. Is NH4OH a strong base? No. Remember, for your bases, they all are elements. Okay? You don't have any polyatomic ions that form a strong base. Okay? It is literally your periodic table. Lithium, sodium, potassium. You kick over here, next to potassium is calcium. Strontium barium. You can help me out. Okay. There's your strong. Add OH, and you've got those. She's right there. Thank you. Okay, so you've got these are your strong bases. They're easy to remember because it's just literally the periodic table. Okay. You get to calcium, you get to potassium, you kick over, and you grab the next 3 down. Okay. You gotta go. There's signs. It's your counselor. All right. So if I look at NO3 then, is HNO3 a strong acid? So we're going to ignore that one. I'm going to take this NH4. It's going to be a plus. What is it going to do? Well, if this is NH4 plus, what is it going to do? Is it going to grab another hydrogen or is it going to lose a hydrogen? It's a base. Okay. So, or it's an acid here in this case. Okay. So this is going to lose a hydrogen. So if it loses a hydrogen, it is going to be NH3. Where did that hydrogen go? Right. We formed H3O plus. We formed and we made an acid. Because this hydrogen is now going to hop over to here and get added in. If you have more H3O plus than you have OH, you've got an acid. You have to memorize your strong acids and bases. Okay?
Wait, isn't SO4?
SO4, yep. If you have H2SO4, the first hydrogen that comes off of here is strong. So if I have H2SO4 and I put that in water, it's going to give me HSO4 minus plus H3O plus. This is a one-way arrow. The first hydrogen that comes off of here is strong. Now, if I take this, and of course it's still in water, it's going to lose that extra hydrogen, but the second hydrogen is going to be weak. So notice my arrow here. So my second hydrogen that comes off of here is a weak. So this is a weak acid. But this is a strong acid. So the first hydrogen that cleaves off of here is going to be strong. So you would have a one-way arrow indicating that.
So in this case, would it be weakened? What, for C?
No. Yeah, this is going to be considered strong because you have this. You have the SO4 2 minus ion here. This is the 2 minus ion. Because this is a -2, this is a +3. If you back up your charges, right? Yeah. So this, when it is placed in water, is still going to remain strong. Okay? So we're going to put that in water. This we're going to just ignore. And now we're going to see what aluminum 3+ does. When I put that in water, what is my 3+ going to go with? What part of this? Your H, which would be positive, or your OH, which would be negative. What part is, yes. So my Al, we're going to form Al plus 3H plus. It's going to leave this behind. If we leave that behind, we've now created what condition? We have more of this, yes. Yes, Maddie.
I don't know if it's the SO4, if it's going to be the strong or the weak one.
It's always, just assume it's the strong one if it's written like this. This is more semantics, okay? Getting into this stuff. This is stuff that you'll get into in college, but I don't want you to go to college and think that both of these are going to end up being strong acids, okay? I don't think that they would ever give you anything like that on the AP exam. That's why if you look back at one of those signs up there, it says you're all going to get ones, okay? When I was talking to them about that, I was talking about this. They're going to give you acids where you only have one hydrogen coming off. I was telling them, oh, you'll all get ones. And they were thinking that I was saying that you're going to all get ones on the exam. And they were just mortified. Like their faces just dropped and they were just like defeated. And I'm like, what's wrong? And they're like, you said we're going to get ones. I'm like, you're going to get acids where there's one hydrogen coming off, not ones on the exam. All right. Let's keep going here. It was funny. It was kind of a funny laugh, haha, laugh moment. All right. Here is a salt as a weak base. So here we go. We are going to take this guy. If we look at this, what is my sodium part of this going to do? It comes from a strong base, so when we put this in water, it's just going to float around in there and be a spectator. Okay, so we're going to ignore that guy for right now. We are going to take our F minus ion that's going to come off of here because HF is a weak acid. Now, it is still very deadly and can cause a lot of damage. So don't think that it's... Well, this can actually, it will actually replace calcium in your bones, and they have to amputate digits and stuff like that. So this is like part of that piranha acid or whatever it's called, if you guys have heard about that on YouTube and stuff. It's similar to that. But at any rate, it's dangerous. All right. So this is going to go, if I think of this as HOH, what part of the HOH is this negative ion going to grab a hold of? The H. So we're going to form this. What's going to be left behind? OH minus. So are we creating an acid or a base for our pH? Base. So your number, your pH, when they want you to calculate this, you should get a number that is greater than 7. It's always a good check in the back of your mind. You may not know what the value is, but you know it should be above 7. So if you get a value lower than that, you probably goofed something. Okay? All right. So we are going to take this and we are going to calculate. They gave us Ka, right? But we've produced the hydroxide ion here. So can I use a Ka when I've produced a hydroxide? What do I need instead? Kb. Okay, so how do we get a Kb from a Ka? We take 1 times 10 to the minus 14, and we divide that by our Ka, and that is going to give us our Kb. All right. Now, we know that we started out with a 0.3 molar solution of NaF. Okay. This is strong. So, and it's also part of our SNAP. So we know that none of this is holding together. This is in a 1-to-1 ratio. So for every 1 NaF that we produce, we're going to have 1 F produced. So when I do that, that means that this is going to be 0.3 molar to start. This is going to be X, and this will be X. So X squared over 0.3. I'm going to ignore my minus X. I'm going to document that. I don't think I need to prove that because this is such a stupid small number. Okay. I'm not going to take the time to prove it to you guys because I don't have time according to Emma. When I do that, I get 2.04 times 10 to the minus 6. That's my molarity, OH minus. I take that, take the negative log. That gives me the POH. I subtract that from 14, and that will equal my pH. I would like you to try to do this tonight and then start in on that chart. Do as much on the chart for homework as you can. This was the chart that you have there. Okay. You can do theoretical here and you can do all of this stuff. You just can't do actual. So don't do the last 2 columns. Okay. And I will see you tomorrow. Paper in your packet, hopefully close to where your homework was last night, that looks like this. Okay, so you are probably familiar with the idea of a dozen, where you've got 12 items. Have you heard of a baker's dozen before? 13. They give you an extra one, like a lot of times during the summer, you'll get corn out at a corn stand, and they'll oftentimes give you 13 ears of corn instead of 12. They'll only charge you for 12, but they give you 13. That way, if there's like a worm in there, or somehow one of the corn ears doesn't, you don't feel like you've been cheated. Okay, so that's called a baker's dozen. That's what they used to do back in the days when you went and got all of your, bakery stuff. Like every day you would go to the bakery and grab stuff. Okay. The dozen kind of started out because it's easily divisible. Okay. If you have 2 people in your family, each person gets 6. If you have 3 people in the family, each person gets 4. If you've got 4 people in your family, each person gets 3. If you've got 6 people in your family, each person gets 2. Okay. And so that's why the dozen was kind of sold that way, because it was easily divisible among the household members as opposed to like 10. It's like, yeah, somebody's getting shorted. Okay. If a teacher tells you to go and get a pack of paper out of the copy room for them, it's a big stack, it's a couple inches thick. It's bound in another sheet of paper. That's called a ream of paper. That's 500 sheets. So these are just ways that we can use to be able to tell you about different amounts. Okay. And I don't remember what a league is. I have to look that up every year. We're talking about sweetest day last hour. So a league is about 3.5 miles. So I just don't use that one very often, so I don't keep that in my mind.
So we can just write approximately 3 points.
Yeah, it's fine. I'm not going to quiz you on this, right? I'm just trying to get you to know that we oftentimes use terms to represent values. Okay? You've heard of 407 years ago. All that 4 would be 80 years. Okay? So we use these to represent things. Okay? The one that we use in chemistry all the time is called the mole. When we are counting things in chemistry, we are counting very tiny things like particles that we cannot see. So we use something called a mole to represent number of items. So it is 6.02 times 10 to the 23rd things. That could be atoms. It could be molecules. it could be people, it'd be a lot of people. Okay. But it could be paper clips, it could be anything. It's a counting unit. But we use it all the time in chemistry. The masses on your periodic table are in grams per mole. So if I want 1 mole of carbon, I'm going to take my balance and I'm going to measure out 12.0 grams of carbon. That's going to equal 1 mole. And I'm not going to sit there and count each atom, 1, 2, 3, 4, all the way until I get up to this. Okay. I can just use my balance to get me there. If you had like a big thing of something and you knew that each gram was 100 items. Okay. So each one gram equaled 100 items. Okay. Would you need to count all the items, or could you just throw the whole container on a balance and get the mass of it? That balance reads 2.2 grams. How many items do you have in there then?
About 200 items.
Yeah.
A little over 200 items.
About 220 items in there. Right? Because 2.2 times 100 would be that. Does that make sense? So you don't actually have to sit there and count each individual item all the way up to 220. You just throw it on the balance, get the mass, and as long as you know this conversion, you're good. Does that make sense? Well, your periodic table has all of those conversions for you. So for sulfur, it says 32.1. Okay. That means that for every 32.1 grams, I have that many atoms of sulfur. And I don't have to sit there and count out all of those items because you'd never be able to do it. They're too tiny to count, right? Okay. And we're going to get into all these different things that we use the mole for later on this year. Okay. So we abbreviate the mole as MOL. I know it saves us a lot of time, right? Just dropping that E off of there. Sometimes it's also a lowercase n. You'll occasionally, I don't know. Just yeah. I didn't make it up. I'm just telling you what it is. Okay. It's the amount of matter in a substance. We also call it Avogadro's number. And that's why back in October, you might have seen we celebrated Mole Day in AP Chem, October 23rd, 10 to the 23. That's how they came up with Mole Day. Okay. I know we're nerds. It's okay. We're fine with it. We've come to peace with it. All right. It's used to count extremely small particles like atoms or molecules. Again, you're not going to be able to sit there and count these out. It's just not going to work. Okay. You don't have that kind of time. So we just use a balance and work it out that way. All right. So we have a conversion factor. This is our conversion factor. So if we have 3.5 moles of sucrose, we can throw that into our dimensional analysis. We know that for every 1 mole of sucrose, we have this many molecules. Multiply across, and you've got your value right here. All right. This is also called the molar mass. Like your molar teeth in your mouth. Molar. Spelled the same way. The The molar mass of any element to its atomic mass has the units on the periodic table. It's going to be in grams per mole. So manganese, if I look that up on my periodic table, manganese, not magnesium. Hopefully you guys have learned that lesson by now. You got probably dinged on that a couple times when you were 54.9. So this says 54.9 grams per mole on the periodic table. I just pulled that right off of my periodic table. So I'm going to set this up. Manganese. What's going to go on the top? Or what's going to go on the bottom? What am I getting rid of? So I'm going to put moles down here. I'm going to put grams up here. Wherever my grams are, that's where the number goes. Off the periodic table. And that's in every 1 mole. So then we just multiply across. 54.9 times 3. That ends up being 164.7 grams. This was off of my periodic table, so don't let that confuse you. I just grabbed that off the periodic table. So the answer is 164.7. Good? Make sense? You want sig figs? Okay, I'll use sig figs. You're right. Good kid. There you go. Better? Better. My bad. All right, everybody happy? Okay. So here we are going grams to molecules. So I'm going to go 1.00 grams of water. I want to get rid of grams. Where do they go? Top or bottom? What's going to go on the other side for units?
Molecules?
I can't get into molecules. I don't have that moles. Yep, I'm going to go moles here. I need to figure out the molecular mass of water. Okay, so we did that yesterday in class. I talked to you about molecular mass. We have our hydrogen and an oxygen. We have 2 hydrogens and 1 oxygen. I get the mass off the periodic table for hydrogen, which is 1, and I multiply across. I get the mass off the periodic table for oxygen, 16, multiply across. And then what do I do? Add. So this is 18.0. My units are grams per mole. So is the 18 going to go on the top line or the bottom line? The bottom. It always goes with the grams. And what goes on the top then? 1. So for every 18 grams of water, I have 1 mole. So if I wanted a mole of water, how much would I weigh out? 18 grams of water. Okay? Yep.
Is it always just like 1, or could you do like 1.0 or like?
It doesn't matter.
Because I don't know if you had to do like 6 on that one, because you multiply.
But remember, these are conversion factors. This is coming off your periodic table. Conversion factors don't factor in to sig figs. It goes back to your measured amount. So your measured amount had 3 sig figs in it. That's how much your answer should have. So anything that goes in here that's going to be your conversion factors, they don't factor into sig figs. Remember that from beginning of the year now? Okay. So always go back to your measured amount. In fact, when I'm doing this in my calculator, I don't round for sig figs until the very, very end. So I keep everything in my calculator, and then at the very end, I do my rounding. Because with these fancy calculators, you can just go up and grab values and bring them down, and then you don't have to retype them in. So if you've got one of these fancier ones, let me know. I can also show you how to store Avogadro's number in here so you don't have to type it in every time. So if you're interested in that, let me know and I can show you if you have one of these fancier ones. Okay, not right this second, but I'll show you. Okay, so I want to get this into molecules. I am not there yet. What am I going to get down here to get rid of? Moles. Do I have a conversion factor between moles and items or molecules? Yes, that is Avogadro's number. And for every one of these, I have 6.02 times 10 to the 23rd of these. And this right here, this number is the one that I will show you how to store in your calculator if you have a fancier one. Okay. So I'm going to go 1 times Avogadro's number divided by, on the bottom, if I have more than one thing down there, what would I need to do? I would need to have parentheses around everything, right? I'm going to hit divide, and then I'm going to put parentheses around all the bottom stuff. All right. My calculator then gives me 3.3444444. I could keep going all day, times 10 to the 22nd. I'm going to round this to 3 sig figs, which is going to be 3.44. And then I'm not going to forget to go back and grab those exponents off of the end. And that's going to be molecules of water. That's an E there. All right. Now, when you get to this point, look at your answer and see if it makes sense. Okay. If I have a gram of water, I can see a gram of water, right? Can you see a gram of water? Okay. People oftentimes forget to write this stuff down here, and they will literally give me this answer. Does it make sense that you would have 3.44 molecules in something that you could see with the visible eye? No. So at that point, if that's what you've written down, you've probably messed something up. So go back and kind of, you're not going to be able to double check your actual answer per se, but does it make rational sense? Okay. If you get to the end and you had a gram of water that you could see and you only had 3 molecules there, that doesn't make any sense, does it? Okay. So think about your answer. This happens every year. I'm telling you, every year. All right. That I think is easy. You can do that one. Okay. Atoms. I want to do this one. I want to do number 6. 6.02 times 10 to the 24th. This is going to be atoms of bismuth. All right. I want to get rid of what? Atoms. I'm going to take that into what? Moles. And I know for every 1 mole, I have how many atoms? Okay. There's a mole right up above Lynn and Ava there. See? If you forget the number, it's there. All right. Now I want to get rid of moles. And I can go to molecules. Or not molecules, atoms. My bad. Atoms. No, I don't want to do that. I just did that. I want to go the other way. I don't want to get into. I want to get into what? Grams. Yeah. That's mass in grams. Bad lippy. All right. Where am I going to get this from? Periodic table. So I'm going to look up bismuth. It is number 83. Its mass is 209.0. All right. Do you remember how to put this into your calculator? You should have an EE key there. For most of you, that's what I want you using. I want you to hit your 6.02, and I want you to hit however you activate that EE key, and then I want you to type in 24. Do not put in times 10 to the EE key does that. If you do that again, you will get the wrong answer. Okay? So this is what you're typing into your calculator. You're going to multiply that by the 209. You're going to hit the divide key. It's a good practice to be in after you hit that divide key, hitting a parentheses. Although if you hit the EE key, it's not going to matter on this one. But EE23, end parentheses, and hit your equals. What did you end up with? Did you get 2090? Do I want to put a decimal here?
No.
No.
No, because that would give me how many sig figs?
4.
And I only need
3.
And with this 0 being there, I just have 3 if I don't put a decimal.
Oh, grams.
Can't have naked numbers. I got to put their units on there. Don't want them running around naked. Get in trouble for that. That's some nudist colony. Come on, y'all. All right. How are you feeling about that? Can I see your homework for tonight? Your homework. Let's see your homework for tonight. I just want to see how far I need to go on this. Grams. Okay. Atoms. Yep, there is an atoms one on there. I wanted to make sure. I wanted to see if I had one of those on there. Yeah, I want to do this one. All right. So we're going to skip to number 9. My answer keys for the notes have all of this stuff on there, I believe. So if you want to go back and work on some of these on your own independently, feel free to. Or if you have questions, we'll work through some more with you if you need it. Okay. So this is going to be grams of aluminum sulfate. And I want to get into atoms of oxygen. Okay. So this is going to be a 3-step conversion. We're going to have 3 different steps that we're going to have along the way to get to the answer. Okay. You ready? All right. The first thing I need to do is get rid of grams. Where am I going to go to get rid of these grams? Okay. I need to go into moles. Where am I going to get my numbers from then? Periodic table. Remember, this is in 1 mole. I'm going to get the values out of the periodic table. So aluminum is 27. 27 times 2 is 54. My sulfur is 32.1. So 3 sulfurs is going to give me 96.3. And then I need 12 oxygens. I can't do that in my head, you guys. Sorry. 32.1. Yeah, I got that right. So 16 times 12 is 192. I'm going to add all of these together. And that's going to give me 342.3. So that's the value that I'm putting down here for this first conversion factor. All right. Then I need to get rid of what? Moles. So I'm going to put moles on the bottom, and I'm going to go into what?
Wait, what? 342.3?
Yep. I had 54 from the sulfur. Or the aluminum, my bad. 27 for aluminum times 2. 27 times 2 is 54. My sulfurs, I had 3 of them because 1 times 3 is 3 at 32.1. That's going to give me 96.3. And then the oxygens are going to be 192. And if you add all that up, it should come up to 342.3. Yes? 9 and 6 is 5. Oh, no. No, 9, 8, 9, 10, 12. Yeah, it's 12. Carry the 1. 9 and 9 is 18. 19. So that's a 4. Carry the 1. Yeah. Yeah, that's what it ends up being. All right. Good. So I'm going to go moles into what? And this is where it's going to get a little difficult. Maybe.
Molecule?
Yes. Very good. Okay. So I have, this is the mass of all of this. Okay. So for example, let's say that I had a car. I had one car. So this is like one car here. And I wanted to know how many wheels we had and how much the wheels weighed. Okay. How many wheels do I have for every car? If you don't take count the spare. 4. Okay. So that's what we're doing here. They're telling you this is the mass of all the cars. Now you got to figure out the mass of the wheels with all those cars. Okay. So we've got one of these. So 1 mole. In 1 mole, I have 6.02 times 10 to the 23rd molecules. They didn't want to know molecules. They wanted to know atoms. So for every molecule of Al2SO4 3, I have how many atoms of oxygen? How many atoms are in each one of these of oxygen? 12. I got that from the formula here for oxygen. Now, if they would have wanted to know sulfur instead of oxygen, what would this number have been? 3. If they would have wanted to know aluminum instead of oxygen, what would this number have been? 2. And that's the only difference between those problems. Okay, so let's calculate our answers here. So we've got 6.04 times Avogadro's number times 12 divided by our mass, which if you have a fancy calculator, remember you can just toggle up and hit enter and it'll pop that down into your equation so you don't have to retype it all, and hit equals. All right, I ended up with 1.27 times 10 to the 23rd atoms of oxygen. Now, if I would have just written this part down and ignored this, would that have made any sense at all? That I would have had less than 2 atoms in a 6-gram sample? go back and double check your work. Does it make sense? Okay. Your moles will always be less than your grams. The only time that they're equal is when you're dealing with one hydrogen. Otherwise, it's always going to be less than every time. Okay, so keep that in mind. If they're asking you to do a problem, come on. Like this, your answer, they want you to determine the moles in this. Your answer will be a smaller number than this value, always. If you're going from grams to moles, it's always going to be smaller because your molecular mass is per mole, grams per mole. So keep that in mind. It's always going to be smaller. So it's a good way to kind of double check your work. Okay? Questions? All right. You need to have a pencil out, and that should be all you need. Oh, a calculator. You'll need a calculator. I needed a calculator for it, so I'm sure you will too. Not for all of it, but for some of it.